Yeah. You can start. Unmute the thing. Don't forget.
అరే మైకి రా స్టార్ట్ చేస్తారు
Teleportation. I got all your attention, didn't I? So, well, I know what you guys are thinking. You guys are thinking about teleportation that they show in the movies, where they teleport a person or stuff halfway across the globe. But that's all just sci-fi. Where's the fun in that? Let's stick to something weird. So now we are going to talk about teleportation of information. Well, everything works out just fine on math, but in reality, there's a villain. And here the villain is something called noise, which is the disturbances and variations. So, well, here there's something called no clone theory. So basically, what the theory states is it is impossible to replicate qubits and duplicate them completely. So, how do we transfer information and states so easily through large distances? Now, my friend Harshit will take over and he'll give you a few prerequisites and basic knowledge.
So what is the basic difference between quantum computing and classical computing? Classical computing uses bits, either 0 or 1. But quantum computing uses a superposition of these bits called qubits. And these qubits can be entangled and which can help to create correlations which are impossible to create in classical systems. And using this, we can create various secure communication and quantum computing. Yeah, so what is entanglement? Basically, entanglement are two separate systems coming together to form a single system. Measuring one instantaneously determines the state of the other. And that's also called as a bell pair. A bell pair, there are 4 bell pairs which exist in a 2-bit state called psi1, psi minus, and phi 1, phi minus. So they are maximally entangled states which serve as quantum channel for teleportation. As I said, there are 4 bell pairs in this 2-bit system. These are the 4 bell states: psi 1, psi minus, phi 1, phi minus. And they have equal probability. As you can see, 1 by root 2 for state 0, 0 and 1, 1, and they are equal probability basically. That's all. This box is done.
Okay, so in this slide, I'll give you a basic overview of what happens in quantum teleportation. So first thing, okay, so here let's assume 2 people, okay. One is Alice and one more is Bob. I don't know why those names are there, but they're everywhere, so we stuck to them.
They're ABCs. That's all.
Oh, okay. So yeah, first step is the state preparation. Alice prepares a quantum state to teleport. So basically here we are taking it as sketch psi, which is the state that we want to teleport to Bob, who is the receiver. And then second stage is the well pair creation, where we use a few gates to create entangled pairs, which is shared between Alice and Bob. And then third stage is the measurement. Alice measures her qubits and sends classical bits. Fourth stage is the correction or recovery. Bob applies operations and brings back the Ketzer. So this is our very beautiful quantum circuit, and here are all the steps. Now I'll tell you in quite a bit of detail. So first we initialize qubits. Q0 is the Ketzer which needs to be teleported. Q1 is Ket0. Q2 is Ket0 again, which is related to Bob, the receiver. Step 2, create a superposition using Hadamard. So yeah, we apply it on Q1. We get Ket0 plus Ket1 whole by root 2. Then we create an entanglement using C0. So basically, we take Q1 as a control and Q2 as a target. We make an entangled well pair with these two, and then we apply C0 to Q0 as control and Q1 as a target. This makes Ket psi interact with the entangled pair, and information spreads into the system. Then then we apply Hadamard gate on Q0. So this converts the state into well measurement basis. Now comes the crazy part. So now Alice measures her qubits. So what happens when you measure a qubit? the superposition breaks and you get classical bits, right? So Alice gets two classical bits, either 0, 0, 0, 1, 1, 0 or 1, 1, and the original state is destroyed. Now she sends these classical bits to Bob. As you can see, there's two lines representing the classical bits in the diagram. And now is another crazy part where just by seeing the first two qubits, first two terms of the qubits, you can apply gates and get back the original case set. So when you get 0, 0, you do nothing, and when you get 0, 1, you apply the X gate. When you get 1, 0, you apply the Z gate, and then 1, 1, you apply X, then Z gate. So then you get the final result, which is the gate side, and then teleportation is successful. Now Harshit will take over.
So after the teleportation, here are the results. So in ideal teleportation, the fidelity is 1 or 100%, which means there is no noise or no interference from the system. And here the measurement outcome is 50%. That is, the outcome might be 1 or might be 0, depending on our original state. Yeah, so noise. So why does noise matter? See, quantum systems are very fragile and very weak, and they can have a very drastic impact from even the smallest to the smallest interference. So in real world, current quantum computers suffer from significant noise and limiting computation, which limit computation time and require highly time-consuming and energy-consuming error correction techniques. So here's a depolarization noise model which we have implemented in our code to simulate this noise in real world. So P here is the probability of noise. So and then which affects the qubit, and the probability P, as the probability P rises, the qubit loses its quantum information and becomes completely mixed. And here is the simulation setup. We have done it using Qiskit, using a 3-bit qubit with measurement and noise channels operating. And one more thing before the fidelity, there are multiple types of noises. There is noises which convert, there are called damping noises which convert 1 over a period of time to 0, and then you have measurement noises which doesn't measure the gas properly, and in cases of 1 they're going to give 0, and in case of 0 they're going to give 1. And here is fidelity again. So what is fidelity? Fidelity is the measurement of success in teleportation. Basically, they check how two states are similar. And if the noise is 0, the fidelity is usually 1 or 100%. And here's as fidelity decreases, noise increases. Basically, that's all. And here is a video of a simulation.
So here we have a live simulation of quantum teleportation using block spheres. So we have 3 block spheres here. The first one is Alice's block sphere, which represents her state, and then second one is Bob's, and that is in the ideal case where fidelity is 1. So basically, it is properly teleported. And third block sphere represents the noisy noisy case of the block sphere, where teleportation is not exactly proper. So Harshit will take over.
Yeah, so these are some real-world applications of quantum teleportation. These are quantum internet and quantum cryptography. So in these are very highly capable and highly secured internet across the world and different quantum computers. The thing is, even the slightest interference can break the quantum bits and degenerate them back to zeros and ones. So people can easily detect them and find where the bits have been occurred across the world. And it can also be applied in this highly precision timekeeping also. Yeah, that's it. Thank you.
Thank you.
Okay. Fine. How do you use it in encryption? Do you have any idea how I'm going to use Okay, teleportation. How is it used? Encryption. Yeah.
Encryption.
I guess entanglement.
Yeah, right. How?
Yeah, basically, teleportation also, because when we use pseudo-random number generators and all, if we know the seed, we can easily get to know what the sequence is, and people who want to break and get to know what the sequence is, they can easily do it. But when we use quantum teleportation, it's like unpredictable.
Teleportation.
No, entanglement.
How does that help with randomness?
Entanglement offers very fast.
Yeah, because when you try to measure it, it breaks down. It becomes classical bits.
You're there.
Yeah.
Okay, fine.
You can. So what I mean, if you want to go back to the circuit, if that helps. You have to send one classical bit right from the sender to the receiver in order to apply the right weights to like on the
Classical bits, no. We get two classical bits when measurement happens.
Yeah, when you're measuring, measuring with like weights, the x and z, the powers are given by given by a classical bit that comes in. I don't know the diagram, but the one I had looked like a different. No, the one I had is slightly different with classical bit coming in with the x and z. Okay, wait, no. I got it confused.
Okay.
No, there only go. Like,
Yeah.
Okay, see, okay, let's look from the right, okay?
Okay.
See the Z and then the bit flips like X.
Yeah.
They are being controlled.
Huh.
While being controlled, can you call it teleportation if that classical bit ka data is going in? That classical bit has a transfer speed that's limited, no? That
Yes.
cannot be transferred.
Exactly. That's the point. Quantum teleportation is not faster than light because it uses classical bits.
You mentioned it was instantaneous. It's not instantaneous.
Not always.
Did I-
If you're using purely.
I thought it is. That's the X end.
Yeah. Okay, maybe I made a mistake. Yeah, it's not instant.
I'm just messing with you.
It's fine.
Simple question. You said like teleportation might not occur as well. Like, what do you mean by? What do you mean by? What happens if my noise increases? That's what I'm asking.
What qubits will get degenerated, so they might measure the information, they might create transformation.
And do you that graph that you write?
That was
wrong.
wrong.
Maybe get tape of this. Send it to me. I will see if I can figure it out. So even I don't understand why you said only got a fidelity of 1 billion.
1.8.
Yeah. But yeah, that's all. Thank you.
Thank you.
Hello. Good afternoon, everyone. My name is Hannah. And I'm Bhumika. And we are doing electron behavior in metals based on Fermi energy levels. So,
Could you repeat your name?
Hannah, H-A-N-A, Bhumika. So, we're first going to talk about energy levels. So, electrons and atoms have discrete energy levels. This is because when you see the wave equations, you only see that few energy levels satisfy the boundary conditions, hence why the energy levels are discrete. And in metals, the energy levels are quite continuous. This is because those electrons, the energy levels are discrete. When all these atoms come close together, the energy bands come. The energy levels kind of come together and form a band, hence why it's continuous. And electrons fill energy levels from lower energy levels to higher energy levels based on outbursts. So Fermi energy is the highest occupied energy level at 0 Kelvin. So all the energy levels below Fermi energy are filled with electrons, while the ones above don't have any electrons in them. In metals, however, the Fermi energy level is on the conduction band, hence why it's conducting. because even at 0 Kelvin, since it's at the conduction band, there are electrons in the conduction band.
Guys, calm down. Like you guys can discuss again, but like, keep it a little low.
So yeah, electrons are in the conduction band, so they are quite conducting. And also, you only need a small amount of energy to get those electrons to go to a higher energy level, making them conducting. And Fermi energy mainly depends on electron density because as there are more electrons in the bands, the Fermi energy increases. And yeah, Fermi direct distribution. So this talks about the probability whether there's an electron present in that energy band. So yeah, it depends upon temperature and also yeah, there's a formula. Fd is equals to 1 by E power E minus EF by kBT plus 1, where Fd is the Fermi factor. Okay, so there are three cases when E is less than EF. So basically, those refers to the energy levels below the Fermi energy band. So there, of course, we know that electrons are present there. That's why Fd is equals to 1, showing that there are electrons present there. When E is greater than EF, you can see that there are the energy levels above the Fermi energy band. And Fd is equals to 0 because there is no electrons present there. And when E is equals to EF, you can see Fd is 0.5. It basically says that there's 50% probability that there can be an electron present in that energy band. And yeah, this is the graph. So if you see, when T is equals to 0 Kelvin, you get a sharper graph. As temperature increases, you get a more smoother graph. This is because the electrons get distributed to the energy levels. And when E minus EF is negative, basically when E is less than EF, you can see that Fe is 1. While when E is greater than EF, you can see that Fe is 0.
So yeah, now I'll be talking about how temperature affects the conduction of electrons in metals. So what is Fermi temperature? Fermi temperature is the temperature at which the electron's energy will be equal to Fermi energy. So the formula will be EF is equals to kB into TF. kB is nothing but Boltzmann constant. And note that this is not the actual temperature because if we consider the real example of copper and if we use the formula for EF is equals to 7 electron volt, the temperature comes to be 81,000 Kelvin, which is not real and which is not, we cannot obtain that temperature. So it's just the Fermi temperature is, we use Fermi temperature just to show that not all valence electrons contribute in conduction in metals. So there are cases if T is equals to 0, electrons fill the energy level up to TF, and if T is less than TF, that is Fermi temperature, only few electrons will cross the Fermi energy level, but not all of them. And then if T is approximately equal to TF, then electrons having the range of kB into T, only those electrons will pass the Fermi level. So and then case 4, which is not possible in real world because TF is 81,000 as we saw for copper. So this case is not possible. This indicates that all valence electrons don't contribute in conduction. So this is our simulation. The graph is of energy and occupancy is nothing but Ft. And as we increase the temperature, as Hannah stated, the curve will get smoother and smoother, and the electrons from the valence band will pass the Fermi level and move to the conduction band and contribute in conduction and supplying current. Since we know that E is equals to N h by L whole square divided by area, has E is directly proportional to n square. So as we increase the quantum number, the EF also increases, and as we decrease the length, since it's inversely proportional, it comes down and it decreases. And as we decrease the L, the energy level increases. And using this gap, we can tell the difference between metals, semiconductors, and insulators. Since semiconductor will be having the energy gap above 0.5, so we can see that EF also increases. And for insulators, which is beyond 0.5 and 1, the EF is so high that electrons cannot cross the Fermi level. So as electrons cross the Fermi level, they obtain kinetic energy which if we equate that kinetic energy to the Fermi energy, then we'll get the velocity of the electrons which have already jumped into conduction band, where Vf is equals to root over of 2 EF by L. And since we consider the case of copper, we'll get Vf is equals to 1.06 into 10 past 6 meters. So this leads to the electrons in the conduction band are in the state of random motion. So since it gains kinetic energy, it will be scattering in the random motion. So due to this, the mean free part will be of course zero. The net current due to this randomness will be of course zero. So we have to put an external electric current and external electric field. So yeah, to gain the conduction and to gain the current, we have to supply external electric field.
So we can see here. So electrons move from lower energy levels and go to the energy levels above the Fermi energy levels. So when that happens, the kinetic energy of the atoms increase. So due to that, the electrons scatter in different directions. So as the electric field increases, as you can see that the electrons drift in the direction opposite to the applied electric field. And few of the applications are diodes and transistors. So due to doping, the Fermi energy levels changes. So in n-type conductors, the Fermi energy levels go towards the conduction band, and in p-type it goes towards the valence band. And another example is LEDs and lasers. So light is produced when electrons go from higher energy level to lower energy level. So that's why electron transition near Fermi level produces light.
So the conclusion part is referring to Fermi level, we get to know that not all valence electrons contribute in conduction, only those electrons which surpasses the Fermi level, they only conduct, they help in conduction. And moreover, if we see the gap, we'll also get to know that Fermi level, if it is inside the valence and inside the conduction band, then it's obviously easy for the electrons to surpass the energy level, and hence we see easy conduction in metals. And in semiconductors, the level is in the band gap, in the middle of the band gap. So hence we require more energy for conduction of electrons, and in insulators, the level is deep inside the conduction band, which we have to supply lot more of energy to see the conduction of electrons. So, yes. Thank you.
Go back to the first GUI program. Do you think tunneling can be? Okay, the Fermi level is a gap of energy. But if you look at a basic tunneling example in drawing, it's basically saying if a particle with energy E comes from higher energy. So is that similar to this? Because the gap can be considered as infinite.
And we can, as mentioned, if T is slightly less than TF or it's approximately equal to TF, few electrons can surpass the Fermi level, and that's how it is equal to energy.
Thank you.
Everybody, guys, whoever is done with their presentation, they can go to Hornbill. Okay, the snacks are set up, so you guys can go right now. Who are done with their presentation? Okay. The four of you can leave. You guys can go to Hornbill. You can have your snacks and then come back. Okay. You guys can go right now. And the volunteer also, if you want to go. You want to go. Okay, then Manasi, what? Okay, I just haven't sent her. Okay, I got one.
Hi guys, my name is Nishita, this is Neha, and today we're going to talk to you about quantum teleportation and noise. So I know you all already had a presentation on this, but I'll try to make this as interesting as possible. So, I mean, when you think about teleportation, it kind of sounds like sci-fi and stuff. And like in your head, you would imagine that, oh my god, like this person disappears from here, like literally appears here. But the thing is, in quantum, it's slightly different from that, and it's quite interesting. So we'll get into it. But before that, I'm going to explain a couple of things to you, so like to help you understand this concept better. So before we even talk about like quantum, like teleportation, and all, let me explain to you what exactly quantum information is. And it's really simple. It's just information stored using quantum states, as opposed to classical information that's stored using classical states, which is 1 and 0, aka like the bits you know, right? So why do we need quantum information? It's because it encodes more information than a classical thing, and therefore it's needed for like more advanced computational simulations and calculations and so on. So yeah, we'll dive into the basics of quantum mechanics and quantum physics.
Okay, so I'll be I'm Anna and I'll be talking about Day-6. So here I'm presenting that basic unit of quantum information is represented either as Ket 0 or Ket 1. It is a class which is a combination of those two, and that is called superposition. We have an example of a simple the general qubit over here, and one important function of one important mechanic of it is measurement. This allows you to get the uh, this allows you to get the transfer from qubit as a class of this function. Qubits are special in the case that they contain phase information. During measurement, you collapse this into classical bits, which is what we use to analyze. Another important function here we here's entanglement is when two bits are very strongly correlated, as in they cannot be represented as independent states, and this allows them to share state, not share state. But like their state dependence on each other, no matter how far away they are. This is the most important concept in quantum distribution. Here we have one of the simplest. Here we have an example of entanglement, which is a real state. This is the general formula.
Okay, so now we get to what exactly is quantum teleportation. So essentially, we're trying to transfer a quantum state from one qubit to another, right? So it's important to understand that there's no transfer of physical matter or anything. We're essentially just transporting the state of the qubit by exploiting the concept of entanglement that she explained earlier. So there's just some important things to note here is that there is no cloning of information, as in like what happens is the state of the qubit gets destroyed at the sender side and essentially gets reconstructed at the receiver side. So we obey the no cloning theorem by making sure that there's no cloning of information, it's just deconstruction and reconstruction. And this cannot be faster than the speed of light. The exact steps will be.
Okay, yeah. So in our case, let's assume a system of 3 qubits that the sender Alice have qubit A, the receiver Bob has qubit B, and qubit Z is the qubit that we want to send the state on. So in the beginning, we generate the graph of qubit A and B, which entangles them, and hence this enables them to share the state. So the next step that we take is that we entangle qubit A and qubit C. So now you cannot represent qubit A without either of those two elements. So then we measure qubit A and qubit C, which returns 2 classical qubits, which we send to qubit B, which then performs a couple of corrections, X and Z on qubit B. So this essentially, during measurement, we destroy the state of qubit C and we reconstruct qubit B in this original state of qubit C. So hence the cycle is essentially teleported.
So let me talk about 2 cases in this. So once the idea, okay, before that, let me just explain fidelity in one line. It's essentially comparing how similar 2 quantum states are. So by getting this measure, so one is like the most similar and 0 is like completely different. So our ideal case here is that the information transmitted perfectly. Fidelity is 1. So when fidelity is 1, it essentially means that there is 0 decoherence. It's like perfect gates, and there's 0 environmental interference, right? But this is not a situation that you can achieve in real life. Real life has something really annoying, and it's called noise. So what exactly is noise? Just to be like really simple, noise is just environmental interaction. So it's just disturbances that exist in the environment that disturb qubits, because qubits are inherently like really sensitive to these kind of things, and even slight disturbances can like disrupt their state. And this is fun fact. This is why quantum computers are like such low temperature, because of noise, right? So yeah, it leads to state distortion and decoherence and reduced reliability. So in our project, we talked about two types of noise. One is depolarizing noise, which essentially introduces like randomness into the state, and amplitude damping is just like it slowly changes the state from like 1 towards 0, and it's basically energy loss. Um,
Okay, now I'll talk about the effects of noise on teleportation. Noise affects the system, and it essentially makes the teleported state unidentical to the original state. This makes the system unable to maintain superposition, and quantum interference affects the radius. This also means that fidelity is lesser than 1 since the original state is just the teleported state. Depending on noise type. Different noises have different effects. Depolarizing noise causes errors, and amplitude damping causes energy loss, which is much more serious. And so you can see that fidelity and the damage done by amplitude damping is much. The fidelity is lesser, and the damage done is more in amplitude damping.
So let me just show you. We've implemented a very basic level of quantum teleportation with a lot of limitations. So I'll just explain how we've gone about this. It's a pretty basic code. So this essentially is the teleportation circuit that we built. So here we're essentially creating a quantum circuit on top, fusing to the quantum circuit 3. So we're creating 3 qubits there, qubit 0, 1, and 2 for simplicity. So in terms of the Alice metaphor, qubit 0 has the state that needs to be that has a state of measurement. 1 is Alice's qubit and 2 is Bob's qubit. So keeping this in mind, we're going to see that we're applying Hadamard. First of all, we're applying rotation y and rotation z on of theta and phi. This essentially creates a qubit of random configuration, and these theta and phi are like inputs. So you can essentially make it into any configuration of qubit you want. For now, it's like fully randomized. And then we're applying Hadamard on 1, and then we're applying C0 on 1 and 2. This essentially creates a maximally entangled bell state between Alice and Bob's qubit. And then after that, we're again applying C0 on 0 and 1, and then Hadamard on 0 again. What this does is essentially apply a bell measurement. And now this state that was meant to be transmitted exists in like correlations between 0, 1, and 2. So what we explained earlier was a different type of teleportation where the original state gets destroyed. And that follows the rules of quantum measurement. Here we've applied something a little different, and it's called deferred measurement, where you can essentially postpone measurement if you're using these controlled quantum operations, and therefore you don't really need to break down the state until like the very end. So now what happens is the state that needs to be transmitted is in existing correlations between 0, 1, and 2. So what we're going to do is we're going to apply some corrections on qubit 2 based on 1 and 0 for like bit flip errors and for phase errors, and this essentially will fix any will essentially align the state and ensure that Z has the quantum state in it. But we haven't measured it yet here. It measures itself later in like a different program. So this is the working of teleportation. We're going to show you the noise models as well. Yeah. So it's again pretty simple. The gist of it is generally we have an empty noise model, and we're creating two types of noise. One is depolarizing, one is amplitude. So you notice that there's error 1 and error 2. That's essentially 1 qubit and 2 qubit error because we're using certain 1 qubit case, which is Hadamard rotate y rotate z, and then we're using 2 qubit gates, which is C0. So to account for the errors in all of these gates, we put error 1 and error 2, and we're essentially creating the noise models by adding all the errors, and we're exporting this. So this is the setup. We'll show you how we run this. So yeah, you see like for every single noise, you can check the fidelity based on the levels of noise. So yeah. So like we'll show you the simulation code and we'll explain.
Okay, so in our non-experiment scope, here we are creating a circuit using noise and analyzing the first to it. And we we have our stacked noise levels right now, and yeah. Here we are generating our random values, and over here is our two cases of ideal and noisy. So here we are taking the state factor, here we are running it. This is so that we can define the current state for the measurement, and this is where we get our final state. This over here is where we are adding our noise to like to the experiment. You get our kind of less kind of noise. Yeah, you're gonna kind of so that is our experiment score. This is our result over here. As you can see, depolarizing has less speed, has a less overall depolarization, and amplitude damping has a very constant, very consistent speed as to its depolarization. This was another example of our results. As you can see, it's random every time.
Yeah, it's pretty much executing every time. Okay, just to top it off, like the cherry on top, we'll talk about quantum communication a little bit, like why do we need it, why is it important, and why is it better than what we have right now. So essentially, yeah, we talked about what it is. So let me tell you why it's better, because quantum communication essentially is way higher security, and it can detect a third party listening almost like automatically, and it's really fast and it's really efficient. So that's why people like really want to implement this kind of quantum communication. However, it is inherently like very sensitive noise and very difficult to implement, and therefore it's like really unreliable. So right now, if you depending on both of them, it's really a trade-off between your information capacity and your security versus reliability. So based on these, you have to. Thank you, guys.
You have a conclusion, right? But yeah, I think get that over in like 2 lines. So yeah, quantum teleportation is, to conclude, it is the transfer of quantum states using entanglement. As you saw before in our experiments, noise is a very big factor in all of this, which is why it is a very big thing to think about in real world systems. And
Yeah, thank you guys. Very well said.
Simple question. Two kinds of noise, depolarizing and ambient. Can you give me examples in the real? Like thermal noise, for example. Is that you think that's depolarizing?
Thermal noise is depolarizing right now because thermal energy is like inherently like random because of entropy, and like that's why entropy analysis. So it just on under.
And do you think that we'll ever get to a point where even if noise is like 0.5, is there a fidelity of noise?
That's hard to say right now. Because I think right now the idea we have of qubits is like I think like from a theoretical standpoint definitely possible to some extent, but I think with our current equipment it's like pretty much impossible to see.
Okay, kind of not true. There's something called holonomic gates which doesn't need. Oh, let's not get into this. It's not true. There's a lot to
ways research.
Yeah.
I don't think I've done that knowledge. Like I have my knowledge, but
they got a Hadamard gate to get a fidelity of 1.
oh,
Yeah.
but
But it's a single.
But yeah, it's a single base gate. And the other thing is they like sacrifice some text.
Yeah, and there's also today there's a paper which was published on Nature in the morning today. For old items which was at 9.
Yeah. Thank you so much.
Guys, we'll wait for this. We'll go to snacks and come back and do
Yeah,
that.
because Hornbill goes in 10 minutes. So if you want snacks, you can.
So guys, let the presentation will be paused. Please go to Hornbill, finish your snacks and come as fast as possible.
Yeah, I'll be
Okay.
here. Okay.
Everyone
Okay, what is that?
Is this tea coffee biscuit?
That. I don't know what wants it, but if you want it, yeah. Let's say,
I'm so sorry. I kept forgetting the audition.
no, but I come up there.
It's this talk recording.
No.
Oh, sorry. Oh, yeah.
There's an actual translation.
How was it?
Hello? Hello everyone, I'm Mohan along with my team Kushagra. We're going to present the noise induced breakdown of growers freedom. I know that's a lot of work, but let's go at it one by one. Yeah. So let's begin by understanding of growers algorithm. Growers algorithm is a special quantum algorithm that takes advantage of quantum bits and how they work to make it so that it can solve the given problem faster. Growers algorithm works very well for NP problems. Does anyone know what NP problem is? The NP problem is the problem where
Please.
Growers algorithm works very well for NP problems. Does anyone have idea what NP problem is? NP problem is the problem where finding the solution is hard. For example, if you're trying to guess your friend's laptop password, it's extremely hard to guess or find. But if you are given a sequence and you're asked, is it the correct password or not? It's extremely easy to verify. In cases like this, Grover algorithm is extremely good. Grover's algorithm has three distinct steps: the phase oracle, the amplitude diffuser, and the iterative search. Now imagine we have a quantum state. Now assume we have hello. Assume we have a quantum state. These are all the possible solution candidates we have for a problem. And as we know, if we measure this, any one of them is randomly given. Before we start Grover's the phase oracle, we make it so that all of these are equally likely. And it is a proven theorem that you can transform any NP problem, which solution can be verified, into a quantum oracle, the phase oracle, where it flips the sign of the solution bit. Solution bit when it's applied on it. And you might think, oh, we know which is the solution bit. This is the solution. If you just okay is our solution, but quantum shapes unfortunately don't work so well. When we try measuring this, it will pop up any one of the random things and we don't know if it's the solution or not. And if your n is large, it's not like you can verify each one of them. This is where the amplitude diffuser comes in. What the amplitude diffuser does is, it takes the average of each one of the amplitudes of this sequence and it flips the state vector along its mean. What it does is, right now all of these are equally likely as their equal amplitude. After the amplitude diffuser is applied, the amplitude of the solution state is increased by a bit, and rest of all the other states are decreased. And as Grover had proved, if you continue this applying the oracle and the amplitude diffuser for pi by 4 by root n iterations, where n is the number of states you have, and you measure the quantum state after all these processes, you will get the solution. It is much better. As normally, if you are going to check all n of them, you worst case you will have to check all n of them to get the solution. In Grover's worst case, you have to check pi by 4 times root n of the solution. You will think, oh, this is very good. So why do you want to normal search? The thing is, in theory, Grover's is way better than normal search if you have quantum system working. But as you know, in theory, 1 week is enough for any exam. Theory and practice are very. The issue we run into is noise. There are many sources of noise for quantum bits, like environmental interferences, the fluctuating electromagnetic fields around the atmosphere, the thermal noise or lattice vibrations causes the gates to behave in a different way. Even the gates, even when there is no noise, the gates aren't always perfect. They might give an error in the measurement, they'll give an error in the reading. And decoherence. Quantum bits, like most of us in class, don't like to sit still. If you leave them alone, they interact with the environment and collapse into states. This is called decoherence. All these things cause the accuracy of the algorithm to decrease. If it's too much, it might cause a bit other than the solution bit to be flipped, which basically invalidates your whole algorithm. So, to see how noise affects a Grover's algorithm, we injected noise into our simulations. A normal single quantum gate has a decent amount of noise in it. but there are more complicated gates called derived gates or 2-qubit gates. They have a lot more noise as there are like multiple single bit gates stacked on top of each other. And we add all this noise because in computer we can't, there isn't any noise inherently, it works ideally. But to simulate the physical system, we added the historical averages of the normal noise. This will tell us how good a gross algorithm actually performs when you use it for actual qubits. Now hand over to my friend Kushag, who will give you a demonstration of the gross algorithm code.
Good evening everyone, Kushag here. So now we will be looking at the simulation and the setup with Quizlet over here. So first of all, we'll be simulating a 2 and 4-bit quantum system and applying noise to the algorithm in that. So as you can see here, the red line, it is representing the probability of getting the right number from the list of numbers when we are searching for it. And the blue line represents the probability of getting that number through the Grover's algorithm. So as you can see in the start, the Grover's algorithm has a much higher probability of getting the correct answer rather than the classical one. However, as he explained, there are noises in the real world, and therefore, due to that noise and errors, the probability falls. And at a decent noise, 0.1 or so, it becomes practically useless, and it is simply faster to just do it in the classical way. Yeah, so this is for a 2-bit quantum system. So as you can see, there's a decent region where you're getting a better speed up, but nobody's using a 2-bit quantum system. It's like nothing. So they actually use 4-bit, larger bit quantum systems, and if we simply go to just a 4-bit one, you can see there is such a huge fall as like just a little bit of noise, 0.005 and 0.01% noise. It is completely making it useless, and it becomes faster to just do it the classical way instead of the quantum way. So this is the biggest issue with Grover's algorithm and like any quantum algorithms in present time. Now, we'll be looking at how this noise actually happens. So, first of all, if we have a large data set, then that is the first way, like more entries, more qubits. So, more qubits will be changing, more errors can be caused. Then the second layer is when we are iterating through the algorithm, we are making changes continuously to the qubits. And every time we change, since it's real hardware, there can be issues and errors in that, and that can cause noise. Then circuit depth. So the more complex the algorithm, the more the changes are iterations, more circuit depth, more changes and more applications on that. Noise compounds. Instead of just increasing linearly, it compounds a lot. And that is why in the previous one, like even with a little bit of noise, it was just gone. Then execution time. So the longer the qubit is we are working with it, the higher the probability of it changing its state due to decoherence and other factors. And yeah, that's just decoherence as you expect. So noise is from that too. Yeah.
Just show the code, I think.
Huh.
Bro, out of the box, like random question. Bro, that means such a wallpaper. Yeah. Thank you.
Extra words for wallpaper.
Where do you get it from? No need, no need.
No.
No, it's fine, I don't want it. I do. Colleagues. Yeah.
You for a school club as a man.
Start. Yeah. Yeah.
Windows key.
So check if it is duplicating, extending, or whatever. It might be extending itself. Duplicate.
There are those more, yeah, they're duplicated.
Yeah.
That's that extended. What is it? Command F1.
Oh.
So So let's start. Administration. Hello YouTube.
Now I'll be explaining the code over here that we are using to simulate the whole thing. So the first function over here is the oracle function that is multiplying by -1 to the correct one. So first we have applied an x gate to the whole data set, and then we perform the function of the oracle, which flips the bit and multiplies it by -1. And then since we had applied an x gate earlier, when we apply a second x gate to reverse the effect of that first x gate. So this is the oracle, the first function. Then this is the diffuser over here. And as you can see, there are because so many gates, because of which the noise continuously compounds. So this is the and in this we have first the H gate and X gate, and then so that we can like rather than we are reflecting it after that. So the edge gate makes it so that everything has an equal probability of getting the right answer, and then where after only the yeah. Then now we are calling the diffuser and the oracle in the main Grover's algorithm, and here over here.
Guys, 2 minutes you had, 1 minute you lost.
Yeah, exactly. And this is the
You don't have to go line by line.
oh, and this is the part where we simulate the noise, and here we are adding the error due to the gates, various gates. Like you have, since some of these gates, they are all basic gates, and some of them are compound gates that you get from these basic gates, and these are the noise with basic gates. And yeah, that's that.
As you can see, theoretically quantum algorithms are directly superior than regular algorithms, but all the circumstances, situation, and technology needed to achieve that speed up is hard. That's where the future is for quantum technology. If you make an error function that corrects all the errors of the quantum technology, no one will be using a classical algorithm for anything. Thank you.
Thank you. Thank you. Quickly asking, who's in girls' hostel here? Okay, yeah. You should have told us this before. Yes, you guys come first. Oh yeah, you guys are done. Okay. The other two things, please present fast. Those who are done can leave. Yeah, by the way, you can leave this one. Okay. Country like yeah. The last question. How many? 4 and 6, 5. Only 5 and 6. And then you guys, right? And then them, and then those 4. Huh? 2. 2 more teams. Yeah. Joy, if you need to get one, scroll in there, you can plus or minus it. On the camera, so you can be there. Okay, don't mess with it, don't mess with it. It's fine. Yes, go ahead.
So hi guys, I'm Sanjana and this is Shrujana. And today we'll be speaking on a project which is an agentic AI legal assistant for Noether. So our basic problem statement is to help people filter out and understand legal cases and legal procedures better. So you give a case and it'll give you more details about the sections and relevant sections and cases. Our solution for this problem statement is to use a RAG pipeline, and we decided to do this because we used a normal general purpose LLM there are possibilities of it hallucinating and giving fake information which we do not want, or it can create new laws which do not exist. So instead, using a RAG pipeline helps so that it's like providing our agent with a law textbook, so it reads from it rather than memorizing sections, so there's less probability of it giving fake laws and making up new laws.
So here is the workflow of a project. So for now, we have taken a small data set. So we are using our Python libraries to convert the text into little chunks, and then we're not training a model here. We're taking pre-trained models from Hugging Face, and then we are putting those vectors into our Chroma database. So whenever a user gives a query, we apply cosine similarity on the query vectors and chunks which are in the database, and then our LLM Gemini gives the final answer to the user.
So the main query part, the search part, happens in two phase pipelines. The first stage, it picks up the query, converts it into vectors, and we use two encoders. First is the bi-encoder, which is the normal cosine similarity function. So that will give us a certain level of similarity, but to increase the relation with the context, we run a second cross-encoder model.
Like, what are you using to correlate the context?
We're using, see, the first normal bi-encoder converts into vectors and normal cosine relation function does. The second one is another model. It uses a different mathematical function entirely. It uses something, it's basically, instead of converting into vectors, it uses something else called the CSL tokens, and it checks word by word with the query and the text, and it gives the output in a probabilistic similarity between 0 and 1 instead of vector output. So it basically just gives more contextual and logical similarity. So it's like two stages, so it's more similar. And the major difference between both of them is, firstly, we're using the bi-encoder because it's more useful on large data, and then we get the top 24 similar results on which we apply the cross-encoder because it's harder to apply it on like larger databases, so we're figuring it out and then apply the cross-encoder.
So main LLM model here we're using Gemini 2.5 flashlight because it's known for its compatibility and low latency. Here we don't have any SDK densities. First, we are using our Python library called URL which will handle the API handling. And then we are limiting our prompt structure to 8 terms so that it's easier for the Gemini to have the context of what the user is asking. And our temperature attribute is set to 0.2 because if you set it to high, it's more prone to hallucination. And then we are limiting it to 4 attempts so it prevents the user from spamming the server. And we are putting a hard constraint in our system prompt. So basically, if I ask something related to divorce, but my database doesn't have it, so I don't want the AI to make up a new law and give the result based on it. So to prevent that, I'm using that. And then, so yeah, okay,
Is hard constraint the only safety that you have?
So,
is the constraint the only safety that you have?
Yeah. So yeah, we have a basic model working, but we have a few limitations here. First, we use pre-trained models from the Hugging Face. It's not trained on the legal text yet, so it might not be that accurate. And our PDF chunking, the thing is, we've used recursive text splitter, which means it splits after a certain recursive count. But our so the problem is it might, if a legal law is there, it might cut in between, so that might cause an issue. And then we're using free trial of Gemini, so which will limit the number of trials. So we have a basic working model. So it gives you the legal laws related to it. Yeah, so it like from all these sections it
sees and it gives it. But like, if I want to check it,
Yeah.
if there's something which is not, if it's not in the database, I don't want it to make up a law, so it will give the result as it's not in the database or something.
There's a dog there on top of top. It's fine. It's fine. You get it. But okay. Yeah, right. That makes sense. Yeah. Can you scroll up?
Yeah.
Okay. Oh, no, that's not actually. Oh, exactly.
Wait, so you upload the
We
textbook and then it
yeah.
Can you show your?
show the text?
Yeah.
Oh, wait, so now does it when this happens, does it remember that it's giving you this information?
It does. Like,
So will it hallucinate?
No, does okay, obviously German has a context system, but are you sandboxing it to that particular scenario or are you moving it consciously?
Yeah.
for like a limited number of attempts, like for the conversation, we have limited it to 8 conversations. Basically, 8.
So it understands the basic context of what you're talking about.
Okay, yeah.
Okay. I mean, okay, that happens. You have to change it.
No, it's not really. It's like usually legal process can be divided into something. Maybe you can have more detail.
The only issue here is legality. You have to ensure
No,
that
the more safety.
yeah. So like, there's certain legal documents that are legal to be put
Correct.
on this. Like for example, if I'm asking a question like this, but I'm asking it because I might have a client who's committed that theft, right? It might break principles of law and
Hey, Noda.
It's only given in what section. It's not like giving.
So,
So
it's basically like you have a bunch of books, you have all the data, so you don't know like where do you search from the book.
Yeah, exactly.
You just get it.
No, this is good enough.
Yeah, that's fine. Got it. It could be like an AI assistant for a lawyer or something.
Yeah, exactly. We can't fully.
yeah.
Oh, that makes sense.
Next, laws of city.
So our project is static binary disk compiler. Our project is static binary disk profiler. Static analysis is fast but fragile, and sandbox is deep but slow. So our security teams are there. You know, they are confused between choosing speed and accuracy. So our malicious malware detecting system doesn't force this choice. Why static malware detection is broken? Because there are like 4 problems. They are brittle. It's like for the file, if you put like 13-byte jump to it, the classifier doesn't consider it as malicious. It will pass through the classifier and it consider it as safe. Thus, it makes it as single as benign and it will pass a classifier. And false positive, it is like all the alerts you get in a day is 30 to 60% alerts are wrong. And blind to packing is that the file is encrypted and it looks like gibberish, and the ML detectors have zero robustness. It's like it doesn't maintain the performance when you encounter unexpected perturbations. Static analysis is that it will only superficially consider the superficially analyzes without running the file, and it has low evasion resistance, and it has a fast speed but low depth, and it doesn't have so much accuracy. On the other hand, Sandbox has mid-level of evasion resistance, and it takes the file and takes it to the isolated environment and goes through the file, and it differentiates between benign and malicious. But our approach has high evasion resistance with the high depth and mid speed.
As we have discussed above, packers and false positives have solutions that we came up with. So the solution is entropy detection plus flagging it as being suspicious. And for false positives, it's confidence scoring. We can show it later on the website. And it's uncertainty flag. It will give you a human review if it's between 40 and 60%. And adversarial ML is like it is a certification testing. It's if a small change flips our prediction, we flag it as like that. Yeah, so this is how our adversarial machine learning works. So we take the file and we just run it like 10 times. And then each time we run it, we're going to make small changes to the file. And it's going to test those 10 times, it's going to test the consistency in it. And then depending on it, manipulate the flag. And then if it's malicious in the end, you just can escalate it into a sandbox. This is...
Yes. Okay. What's the threshold levels for pushing it to sandbox? How do you decide? How did you
We'll show the... Yeah, but it's not completely sandbox because sandboxing is like too complex right now. But until it's like 60%, it can be like benign. After that, it's like you can push it to sandbox if needed. This was the research that we found out, and that's how we came up with the adversarial ML. So this is our website. If you give a .exe file, import it, this will give the confidence score that is like benign and malicious. Here is the boundary. Boundary is like from 40%, sorry, 30% to 60%. If the confidence score is between 40 to 60, it will be considered for human belief. It's 49. And there is a sharp also. It will tell why the confidence score is that percentage. If it is under human belief, this chart is helpful for the human beings to decide.
prices?
If it is in the boundary, the chart will help the human beings to easily decide why it is malicious or benign. It will just tell you where it is going benign and where it's going malicious, like what the problems are. There are numbers here, right?
Yeah. Oh yeah, there are.
Yeah, they'll show it in a laptop.
No, it's not. I mean, I see them. What's the file size unit? What are you measuring it? 0.8461 to what?
Oh, this is what is that?
Is it a confidence interval thing or is it a?
No, it's just like based on the confidence interval.
That's the file size of
File size is what? 846
of what? And key and key.
No, it's just like confidence interval, like where it is coming, like how much of it is in between this.
Confidence interval 0 to 100.
Yeah, percentage.
Okay, you're asking this.
Yeah, 846,000.
Is it your scoring system?
What's 846,000?
Okay, fine.
So this is like most websites and apps that take this. It gets easily parsed because they don't care about Windows API, right? So that malicious files, they usually use Windows API that can be parsed too. So our website actually flags them to the Windows API, like it goes through them and flags them as malicious one and then 90, and based on that, whenever it just opens the file, even before running it, it will know that it is a malicious. We use graph matrix. It is like the feature from neuroscience computing. We took it in this project because we'll tell about it later. Here, math centrality is like what are the functions. We did like graph features wherein the functions are connected to each other. So math centrality will tell what function is connected to how many. Sorry, each function is how many. Sorry. One function is connected to how many other functions, and clustering will tell how tightly or it is spread out or not. Graph density will tell the ratio between actual edges and the possible edges. Components will tell if it is in one piece or it is fragmented. She'll tell why did we use graph features in the graph features of neurocomputing in our project. As I've already discussed about adversarial, that's how it works. And we've actually seen that the structural identity that's being used for this malware is being used for EEG signal detection too. So this adversarial can actually be running the same, like for EEG signals if possible. But the research is done with no thing on this. Yeah, exactly. Yara code is like it will convert probabilistic AI to the deterministic AI, and it will convert this code to human readable form so that the human beings can understand what is wrong and what is right, and they can use that for the they can export it and use it later. It's like it turns probabilistic AI into deterministic AI and theoretical.
The second part actually can be used for design optimization. Really good. The crafting you're talking about, you can have a really good design analysis system where you use it to analyze how, like just not for just malware, like you can use it for complicated projects where you can reduce your complexity, increase correlation, other systems.
Thank you.
Now bro, not hungry.
How many left? 1, 2, 3, 4. 4 left now. So come forward. George, how are you going now? Tell me if it shows battery low. It does not show battery. know a little bit more.
Hello.
Yeah, 6 minutes. If you want to
So hi guys, today we are doing a presentation on quantum barrier tunneling. I'm Kushi and this is Roshan.
Hi guys, so as you have seen in your physics classes, we learned about barrier tunneling. It was just a rectangular barrier that we learned, but there's more to it. Our problem statement includes the various different shapes of barriers and different particles and how it reacts to. And we also changed the parameters by changing the barrier height, barrier width, or the energy of the particles. That is our basically our whole project right now.
So could you put it on slide?
Yeah, but we have to change the tabs.
Oh, that's okay.
So as we all know, this is Schrodinger's time-independent equation. So solving that, we find that the wave equation is a into e power minus alpha x plus b into e power alpha x, and we can find alpha using that. So using solving a and b, we find transmission probability. For our project here, since we are using different barriers, in our code we have used WKB approximation. So this is the formula, and R will be 1 minus T.
This WKB approximation can be used for any other shape rather than the standard shapes. We got to go to the formula, but executing in our program took a little time, so we'll come up with a formula for now. Okay, first barrier is the rectangular barrier, which is the standard ones that we've learned. It is a simple exponential decay inside the barrier because it's a higher slope, so the reflection coefficient is more, there are higher reflections, and then there's modeling tunneling strength here. The potential is constant, and the transmission coefficient is given by that formula. The application of this can be in Zener diodes where there's band-to-band tunneling from valence band to conduction band. This is our GUI where we show the wave function and probability density, how it varies with position and time. This is with respect to a rectangular barrier, and this is how it changes with time.
So when E is less than V naught, we can see that the transmission probability will be very less and reflection will be very high for a electron. And when E is greater than V naught, then we see that the transmission probability will be very high and reflection will be very high. For protons, since we all know that transmission probability depends on mass and transmission probability decreases with increase in mass, protons will have a lesser transmission probability. Alpha particle and atoms also, the potential barrier will be like a solid mass ball, so it can't go through.
Next is the triangular barrier that we're seeing. There's a gradual decay in the wave behavior because the slope is a linear slope here. And it follows, potential follows V naught minus Fx, so that's a linear equation there. Then there's high tunneling strength because of this. So there's lower reflections at the edges than the rectangular barriers. Wave function is from smooth, from like a wave particle, like free particle, and then transitions to smooth decay. This is called an AD function because the potential gradually decreases. The application of this is a scanning tunneling microscope. This is the GUI part where we show we have different particles like electrons, protons, neutrons, alpha particles, and atoms in this. And in the animation, you can see how the size, that's just the wave function, and the probability changes with time.
So for a triangular barrier, as she said, the electron will move more efficiency and transmission probability will be greater compared to the rectangular barrier. And for a proton, if the slope of the triangular barrier will be gentler, then it can pass through it, but it's the transmission probability is very less. And alpha and atom again will have lesser transmission probability or close to zero.
Okay, next is a circular barrier, which is also called the Coulomb or the radial barrier. Here is very low tunneling strength because the potential is inversely proportional to the radius there. And then the transmission coefficient is equal to exponent of minus 2g, but g is the integral over the curve barrier. Here there is wave function that is gradual decay over a large region.
For electrons in circular barrier, when E is less than V naught, standing wave patterns are formed because the electron waves are trapped inside the circular barrier. And for like alpha particles, this is an application. It causes alpha decay. And then for protons, we know that in the sun, the protons fuse. So like the protons are both positive charge. So classically, they should repel each other, but using quantum physics, the Coulombic barrier, they could tunnel through it and they can fuse through it. So this is one of them.
Here in circular barrier, the half rate, with higher energy of electrons, the half rate decreases exponentially. Next is a Gaussian barrier and the most realistic barrier, which is a bell-shaped barrier. Here there's moderate to high tunneling strength because the slope of the barrier is gentle, so there's no sharp boundary and there's mild reflections at the edges. Then it's a very smooth decay recovery where it follows the formula of this.
For a Gaussian barrier, as she said, for electrons, since there is no sharp change in potential barrier, the reflection will be lesser. And for protons, and since it has shorter wavelengths, it will go to the barrier if it's near where the thickness is smaller or like the width is less. And then for alpha particles, if E is less than V naught, it won't go through. If E is greater than V naught, you can see a steep change and the transmission probability will be 100%.
The application of this includes cold trap neutrons, where which is focused using a laser, and then the tunneling is used as a filter. Next is the double barrier, where there are two rectangular barriers, and there's low tunneling strength, but at resonance, when there's a standing wave formed because of constructive interference, there's high tunneling strength here. So there's more reflections at the edges normally, but when resonance occurs, it's less. The wave function is strong standing waves in between the barriers because when the allowed energy space matches the energy of the barrier, resonance occurs and there's constructive interference. The potential and transmission coefficients are applied by using these formulas.
For double barrier for electrons, the electron energy matches the allowed energy level inside the well. It undergoes resonant tunneling. And for protons, there are some cases where it goes to resonant tunneling for certain chemical bonds, like in DNA or hydrogen bonds.
The application of double barrier will include resonant tunneling diodes. This is the tech stack we've used. We've used Python, NumPy, Matplotlib, and all others, including for our GUI and our logic. Thank you.
Just one question. You guys think the photon in your particles? What do you happens to a photon?
Who's next? Oh, none of you know how to change the battery? Who else is left? You can like tap your stuff so that. So, Bata, how many engineers did it take to change the battery? That's really bad. Just 3 minutes here.
Yeah, you can start. Say 6 minutes.
So basically, my name is Anurag. She's Krishna. We're both first year students in Noether. And
range from 1 to 12. In top that are 5 gates, 48, 45, 48, and so with gates. And suppose I say cinema, and we can use any target. We can target. Suppose we are using 48, and by mistake I identified an input error. So then we can use and for not using a control system target. I choose one the target next so going like and we have an option of barrier which doesn't do anything so stupid. It's just a barrier and we have options of
They use the mic.
What's the barrier? What's the barrier?
it's basically just to separate the gates. Like, because basically what happens with QC is that when you separate the gates, you place it in the same, what do you call it, layer or region or whatever. So you like sequence
Okay,
it.
so at the barrier, that's the state of the barrier.
It's basically like this thing, a wire type.
Okay. Wire? I didn't
Like,
understand, bro.
okay, how should I explain it? Basically,
Bro, wait, can you remove it and put it in like?
yeah, see not good. Yeah. So you can see here, right? We have 2 gates placed in the same area. So what happens is we put a yeah. So when we place a poly X gate, it was actually placing in the same line or layer. So when you put a barrier, it sequences it.
we have C0 gate, right? This, and when we put barrier, there's no change in the qubit.
Where's the poly X now you want me to paste it? You must be point shape.
You get the point.
And at the end, we'll measure the probability.
So basically implementation wise is very simple. All we did is we use a stack to store the different states of the quantum circuit, and whenever you make a change, it updates the stack. That's it. Whenever you have to undo something, it just pops the last element of the stack and displays that. One problem we faced is that we were not able to take the measurement of the circuit because the function that we use in order to display the state vector, when that function is null, then the program crashes, and we weren't able to figure out a way around that. We have to change the whole system and how we display the circuit. So that's basically our project. Yeah.
I think he mentioned that got fixed. You guys fixed that, right? To an extent. I mean, you cannot measure it again.
No, we did not.
You didn't.
We weren't able to.
But at least you didn't explicitly measure and keep the same thing. So that way you're not technically wrong with what you did. Morning you were wrong, and you fixed that. So I think that's a good thing.
Thank you. Yeah, that's a point.
And how are you actually running the quantum circuit? Are you using discrete AR or?
No, this is just regular Qiskit. Simple. T-inter, simplified, mathematical, Qiskit. That's it.
Can you show your package? Yeah, this is your full script.
Yeah, this is
So, show me the actual quantum function that's doing the whole evaluation. Oh, there is my. No, this is also give you matrices of your multiplication. No, have you guys used the Qiskit, the ideal quantum composer?
No.
Try it out, it's pretty good.
The only thing that I would say, I didn't work for like 52.
Nothing works for 50 qubits. I know this is really qubits. But yeah, try it out. That gives you a block sphere and a Q sphere and also.
Anything else?
You can also see computing.ai is a composer. I built the. Yeah, I built Dodge user model for it.
Okay, thank you. Thank you.
Yeah, after
Okay, wow. I'm just joking. Why don't we just come and grab the mic, please? Joy, you're good for mic now? Okay. Are you wearing the earrings?
Yeah, so hello. So basically here I'm Aditya, he's Anuj. So we come up with this problem statement. We are trying to solve this. So basically, like, have you guys ever rode on a roller coaster or something?
Yeah.
Like, man, how much do you guys really pay for that?
How much did they pay for a roller coaster?
Like 10 years.
You don't want to know.
Okay, so yeah, it's like I've been to Singapore like 2 years ago or something. So like paying 7,000 for a roller coaster when you have Bangladesh potholes right in front of you. So okay, so the point is this thing can actually help solve that to some extent. So basically, what if imagine a world where like while you lay the road, you can actually determine the lifetime of the road, like suppose like 10, 15 years or something. Because nowadays, why wait until the monsoon and the potholes randomly form? So this thing kind of, it uses two technologies. One, the vision, which kind of determines how the quality of the material is, right? Suppose what the material is kind of made of, and the other thing is the sound, which kind of helps us understand the internal DNA, right? So you might be asking what's internal DNA for a material. So basically, it kind of tells us all the properties of a material, like probably density or something like that. So, like suppose you can just try this, like we can do it like by our naked eyes, can we kind of determine between the acrylic, this plastic and the glass? It's kind of really difficult unless you touch it, right? So this thing, what we are trying to solve is that just by vision, it's really tough to kind of understand the actual mechanism of a material. So like if you like assume a robot is working in a factory or something, like suppose a glass is like really fragile, right? Like suppose if you apply some 20-30 Newton, it kind of breaks. But at the same time, plastic needs a lot of force or something. So the robot cannot afford to like just by its vision, it cannot misunderstand the glass with plastics. So this is the sound technology we are trying is that like we don't just look, we kind of listen to the internal dynamics of the material. Similarly, the wood and the steel. Like suppose nowadays, generally many people like kind of take steel and kind of use the wooden paint on it. So that it's kind of really tough to differentiate between them. Like and even gold. Gold is really costly. But at the same time, what if I tell you that the density of gold and tungsten is really same and you can actually be cheated by the people of the jewelry or something because the color all you have to do is a polish to the tungsten and you have the same result. So like the next slide. So this is our solution. So what we do is like we train a model so that basically it can detect the texture and from the texture it can kind of tell all the properties like the Young's modulus, the amount of pressure you need to apply so that it doesn't break or something. And at the same time, we are implementing a new technology by adding a sound. So basically, what it does is you can see here, like spectrogram. Basically, sound cannot be perceived by computers in such a good way. So what this does is like it converts the sound. Like basically, suppose like the robot instead of just looking and determining the material, it just suppose taps it and understands the internal dynamics. So that what it does is it converts the sound to a frequency wave, maybe a sine wave, something like that. So basically, based on the number of based on the frequency of the material, it can understand the density or some all the internal properties of it. So we use for the AI, we actually use Teachable by Google, like to just train the model. So what we did is so this is the image model we did. So basically what we did is like we kind of use many you guys have heard about Polyhaven or something like if you know Blender or something, you might have come across Polyhaven and other texture websites. So basically we kind of took images from Google and other things and we just trained a model so that it can identify the type of material. So this is the for the visual part of it. For the audio part of it, I guess he's gonna explain it. And yeah. Yeah, so what we have did, like we uploaded 40-50 images of a particular thing so that it gets trained. And similarly for the audio as well, we kind of even use the plain background so that it understands what the kind of background it is. So we call it the year so that yeah, next. So yeah, this is the first layer, which is the vision part of the model. So basically what it does is like if you're actually kind of deep dive into textures, you'll understand that textures are actually not a single entity, like you have subdivisions in it. Like suppose the chain in here is like suppose you have pixels like RGB, you have heard of RGB, right? So basically a texture, the albedo part is like only the color of it. So like a texture has color, you have the specularity. Specularity is like something like it tells us the like I guess in 10th we would have all learned that we have this natural what do you call that? Yeah, regular and irregular reflection, right? So basically, specularity, what it does is like based on the texture, it tells us that how it tells us how reflective or something a material is, and similarly albedo. So what this does is like RGB, like suppose the main color is divided into three RGB. So what it does is like the computer takes a value for each thing and it plugs the RGB in. There are actually three layers and it's plugged into one so that we get the final image. So then we have ambient occlusion and stuff. So this is the first part of vision. So now what this model additionally does is that we also like once you scan the image, you can also get the roughness of it, the acoustic profile, that is the volume, to know the internal dynamics and the stiffness, the durability, the thermal response, and the hardness. I'll just kind of demonstrate with the website. Yeah, so we have two options here. Like we have the live scanner, which can actually use a phone to kind of detect the material and file upload. I just do a demo run of the file. I suppose I take this. So this is the wood. Hopefully this wood, and yep, with a confidence of 99.5%. Then this is the audio part. I guess my friend is going to explain that. And at the same time, you can get the confidence level of this. Like we can set a threshold for this so that if it's kind of confidence, and you can also see the raw probabilities. So that is the first part, and the second part is going to explain.
Okay, so as he told that the vision is only not like completely acceptable part. So we also care about the sound because it, like as he told, it gives about the internal details. Now consider that we paint maybe a steel object. Yeah, guys. Okay. Okay, so the density of steel does not just change because we painted it. The characteristics of it would remain the same. So now what we do here is we use the tap test principle. So for this, we first train our model by having 20 second video, 20-second audio, so that the model just understands the scenario of the room, whatever. And then we upload sample audios to it and train the model. So next, certain materials like wood or plastic, they absorb the vibrations quickly, and the sound would be like a thud. But then, whereas for metallic objects, we observe the ring sound. So now, we convert these sounds into a visual heat map, and which reveals the material's DNA. So, demonstration. So
I'm not sure if this thing is reading here because I don't know if the sound or something, but in the house it did perfectly work, and I just showed the picture of it.
Press the mic button. Go back to the project.
Yes,
this was the output yesterday, which we got. So this, it was the same wood. So this, it is a heat map showing the, the wood, the surface. So from this, and also I think the accuracy was 99.9. Audio. Go to the audio acoustic verification. Let's go down. Yeah, click the mic. The one next to it. Mic. Yeah. You can allow it and use it happen. See what happens. It's not recorded. That is the recorder. Play it.
Yeah, it did. But I
the frequency. Bro, can you try this instead? Do this next to the microphone. I don't think they are plastic data. What data? What was your data set? Wood.
Yeah, I just showed you, right? We have aluminium, right?
Wait, this is huge. Image data set, audio.
Audio data set, yeah.
Audio data set.
We only
plastic is a
steel, wood, plastic, and
right. It should be. Even it gives me very low. Just a tap. It's cool to it works. Yeah, that's okay. Or reduce the confidence. Put it to 50, 40. Yeah, it's fine. It's fine if it's. No, even pull up. No, it's 50. It's fine. I'm waiting for you. Okay, stop it. I think the thing is going out of bounds. Yeah, I think there's some issue. Okay.
So yeah, I guess we can end it up.
No, we get. Yeah. So
just finish it up.
yeah, the robo would be blind without like all these applications. Now the amount of pressure. Now suppose we are using a material, like a material has to be lifted or something. So now the robo, if you tell that it is glass, then the amount of pressure it would put would be less. But then for steel, it would apply more pressure. So we could also use this model for fraud detection and all that. So for the quality control for road construction and all that, and then we can use it for the extraction of high value metals from discarded circuit boards. We can also use it for identifying which is conductor, insulator, and all that. And then
landfill. This is all there. Big landfill.
Yeah, and this is the material aging simulator, which, as you can see, the chair that is new, and then the chair after 1, 3, and 5+ years, it would look like that. So we could also do this, which could be added.
Oh, it could be added. You're not added.
No.
Okay.
And then all these features also.
Okay, so I want you guys to actually do something. Go further.
Someone put the limit thing is
Your first for your data set, go find an actual data set. Because right now you
Yeah,
guys
we actually find the data set.
Yeah, it was not that.
Actually, we didn't have time. We actually thought of data set.
But now you take your phone and not your second is to take random. Every time you see a phone call or a random thing, take a minute.
That's a chaotic line. It is like
very
oh.
fast. And actually, your first that will help you scale up stuff. You might be able to take this very fast. And see, I'm not joking. With this.
Calm down with all right. Yeah, you guys take your time. It's a good one.
So basically, this was the data set we can calculate and these are some AI data. I guess that's important. So yeah, thank you.
Yeah, thank you.
Phone assembly, the fucking blind factor is used phone assembly. Phone assembly, layout is fixed. Where this robot was fixed. Now I'm talking about a non-blind factory, not a blind factory. For landfill hey, inside the segregation point, not at the landfill.
No, but hello.
See, again, okay, fine. It won't be like close. The segregation will have like because it is segregated. Understand? And then you will definitely have saying this is cheaper.
Yes.
Last week, you have 6 Holy Maga.
You guys can start. I'll just be back.
Can I start? Yeah, okay. So the thing is, my name is Sumanyu and he is Vidit Soni. Okay. So we have built something like, first of all, our domain is system administration, like this admin. And in that, we have built something called as DICE, which is Direct Integrated Control Engine. Okay, that's the thing which we have named currently. So it's similar to, it's I guess it's like saying more than similar, it's better than Siri or OK Google of mobile. Okay, it's an we can say it's an advanced version, but with a bit of little fewer commands. Okay, so the thing is, okay, so the thing is key differentiation in our project and the Siri and all is first it's partially offline, means there are some commands which do not need any kind of internet to work out. The thing is it's AI powered. We have used Olama and out of which we have used Jima 3.1b, which handle unstructured queries and results of all the information, etc. Then screen analysis, which we are using Tesseract OCR, and also we have 20+ language where translation means just by by voice command it can translate from one language to another language. Okay, so this is a system architecture out of which these are the stuff. We have voice engine, voice commands, perception engine, decision brain, and screen analysis, which is Tesseract OCR and context engine. Out of which
out of your perception engine is would tell you the updates about your CPU, like it will give you full complete system information. And voice commands would we have multiple voice commands which will show you, right? And the next is voice engine, which lets you talk. No, second. Okay, so here in data flow process, what like how the things are going to work, let me tell you. So what is getting captured, then there's a specific wake word. Okay, so dice is it's something like okay overall ACD kind of thing. So we say hey dice or okay dice or whatever the thing is, or just dice. Okay, so that's wake detection. Like means that word is detected and the system opens like a small pop-up window opens there, and then we give some kind of command. The command gets matched with what is present in our base code, and then it's processed by AI, and we get the expected result. Okay. So voice engine and wake words. So as I told you, we have some wake words like oh hey dice, okay dice, daisy, plus phonetic variants, okay, and some different type of accents and all. Okay, so screen analyst, which means just if you like from for any kind of web page or just like wherever we can go, we can just tell our dice to summarize the whole page. It will summarize the whole page and give you proper a small summary of what is present basically in the page and all. Okay. So this part is gonna be extended back.
So these are the installation requirements, like what system we need for the requirement about Python deficiency. Like for this thing, we need Windows 10 or 11, and these were the different parts of this. Then we need a works model and API keys. We are using OpenWeather API. So these are the core features of it. This time and date, display, and system monitoring, weather, volume, media, brightness. Yeah, it's for offline and partially offline. It's for partially offline. It's like some commands may work on offline.
Fine, got it.
That's all. These are the additional features. These are timers and alarm, like countdown timers with labels, calculator, all basic additions, subtraction, multiplication, use and etc. And translation is 20 plus languages over there. And notes we can save the voice notes also with timestamp. And the opportunities are like Google and all. Google, YouTube search, and you want to open any command, open any folder, open like search any folder, document, and etc. So
Okay, so thing is we are gonna fastly cover what are the technical specifications and like what we need to build this. After that, we will go to the demo working. Okay, so current specification is we are using WAS model. Before that, we tried to use Google model, but the thing is it was not taking, it was not able to hear what our accents and words what we are saying properly. So WAS model, which is okay, whatever the thing is, and 4,000 samples per block. Then custom ticketed GUI is used in Python, and then SQL-like database is used. To store the data and to store the memory of okay, and then a tesseract and OCR file to read the screen and micro charts and like what are the future things are there. I would like to know. So now I will show you the working. So before that, I just want to show you one thing. We have also built. So we have also built this site where you can just go. It's site is deployed. Model is also deployed. You can just go there and you can download the model. Okay, so you can download the model for free. The thing is currently in my laptop it's installed. So in your laptop you can just install and work it out. Thing is, and also you have wait list and feedback. Okay, let me bring you to the model. Okay, so as a model pre-installed. Sorry.
You have run files and install.
Yeah. From basic complete application, not the AC application. You can just
Dekinter.
Yeah.
Using Dekinter GUI.
Dekinter is just for the
but for the installation, I'm asking.
Yeah, installation also
it's
Dekinter. And just not that, it downloads everything. Like
okay, wait, do we get it? If I install the application, do I have to open it on the PS4 or do I?
No.
So it's an application, right?
It's an application.
On Dekinter.
Yeah, Dekinter GUI is used.
Okay, fine. No,
I mean, I haven't worked.
No, you can, but okay, fine, sure.
Okay.
So, show us the video.
Okay, so it's a small pop-up box.
Okay, that makes sense. what is the auto run file? Can you show us the like system mechanism or pipeline mechanism?
Yeah, I will show you everything.
Yeah.
Okay, so let me first show the working of it. Okay, the thing is,
are you going to make this open source?
we have not yet thought. We will. The thing is, it's already available for downloading. No, I'm not. I am from IEEE APS.
APS, you're EC student.
I'm EC student.
Both of you.
No, I'm EC student. He's from AI. Okay. So I will execute it and show you. And then, as you said, I will show you all the internal requirements. Yeah, it's working. Okay, so here it is. Okay, so this dice point is popping up, and
not played.
okay, so the thing is, from you can type any of the commands directly. Either you can type any of the commands, or you can just say hey dice or the make words and just type any of the commands you want. It will execute it. Now let me show you some
commands are not audio prompted, is it?
The commands also audio prompted. But the thing is, currently it's if you say some kind of command, it takes like the spelling mistakes happen in the commands and that.
Oh yeah, BTS is not good.
Yeah, it's not excellent. It's not excellent, but it does work. It does work. Was model only. Was only. Everything is on was because we first.
Why is like was is good enough? I'm not sure why. What is it a device specific issue or did you try running it on other device?
No, yeah.
Asking because it's actually a good project and you guys can build it for the.
Yeah, the thing is, I tried to run it on one of my parents' laptop. It worked good, but the thing is, even then also it's making some of the spelling mistakes. And for that, I want to show you one thing.
Okay, for that you can maybe have a correlation function for it where you go to the closest word, right? Instead of going phonetically, you can go to a correlation vector, map to a proper, like an LLM system, where you map it to an actual word.
Analyze the current session. The CPU usage is elevated.
Okay, so let me tell you this thing also. So basically, this thing is, as you can see here, as you can see here, you can see the message. Okay, so you can see here polling every 2.2 seconds, which means that it uses all the system information to you after every 2 seconds.
This like you built it before you've been working on it?
We were working on it.
No, we were working it from around 1 week.
Yeah, we had done
One to one
working
to one
on
and a half.
a Mac, and after that.
The thing is, currently this is only for Windows now, but he is also developing for Mac. Okay, so let me execute some few commands on it and just show you. Okay. So I'm just typing in front of you. You can just also learn the voice.
There's a lot of space. What's with the delay? Just saying your CPU is very nice.
The thing is, my laptop is getting too much heat up because everything is working on my laptop and I have CPU and I'm not getting kind of.
So what kind of impact does this have in terms of CPU?
No, it only notifies you that your CPU is working at this much percentage.
In terms of running, to actually run there.
Did you run any weight?
Yeah. What kind of I'm using quantization and you have any kind of what is the minimum hardware limitation?
Like, do you have any hardware specific?
Yeah, like for example, if I were to give this like an array of 59, 10 of them, a total of I don't know 300. It's a personal. What are you doing on 59? Because I did it once. I did it once. Would it improve?
I'm not about that, but it should if you provide GPU, one GPU also it could improve its performance because obviously it's GPU. It could definitely improve performance.
Issue is
so let me show this to you. Okay, I have written a search for Sunil Deshpande, which is my name.
Because you are always recording, there will be a lot of your systematic errors.
And also one of the main factors is there is some kind of ambient noise. That's why it also takes issues sometimes. Okay, so let me take this command. Search for Sunil Deshpande. It's my name. Okay, on Google it will just it will open the Chrome and the first picture is of mine. Okay, so that's the thing. And the second thing is so I will also just tell you about one more feature that's about volume up and volume down. See here, we have integrated OpenCV also. You can just put your hand gestures and through voice and both you can just control volume up, brightness and everything. Let me just show you one mail thing also, which currently Gemini or OK Google can't do. Correct. Okay, they can't do it. So composing it. Okay, so it was asking what's the SME email address. So I'm just okay. So I have used some kind of my email. Okay, a model subject. Okay.
One question.
Yeah, sure.
How are you identifying the task to be done? Are you using API call or is it locally trained model?
No, it's not local model. We have used Olama model, which is completely open source by Google. And we have,
that's fine, but is it Olama local or is it
Olama local? Olama server, yeah, Olama local. And through Quantum, we are running it. Olama server.
Okay. So I'm guessing that if you give it a GPU, the Olama but issue is if you are giving it a GPU or decentralized, you get escalation. Yeah. Because you're using voice, it's always recorded.
Okay, so the thing is, we are not doing that. Okay, so just okay. The thing is, we are for the main thing. It asks me what the subject. I told you for a presentation, and just one small context to it.
This CPU interesting what you're telling to repeatedly tell you.
Yeah. So that is it. Every 2 seconds it will post the message. And what's the trends we use is percentage on. And if you want to specifically know that okay, what is system information, then you can also command which will give you system info and everything. Okay. So thing is here.
Can I give a cluster of commands or are they only some brain commands?
You can just okay. Give me the commands. I will see whether they are
okay. What are commands? No.
Okay,
I go to press to rate my block and it will.
You want to see the
You know, we built this in Classworks. It automatically gives KB 2 stars. 5 stars.
There's some kind of keywords there.
So, for example, if I just open a website, like if I say open session,
yes.
Will it open in Google or?
Okay, so it doesn't give exact URL.
If I try search.
Yeah,
it's an open method. Okay, so see, they have to. The context is
okay, this is nice.
The context is fully not there. Like,
no, but Peso Academy, you are not mentioning. Open is for an app.
They have put open Peso Academy.
Okay, so it will not. Wait, because PesoAcademy.com is an app, it's not an app.
Oh, so okay, so you have open to app.
Open Chrome, like that is
you can also access WhatsApp to it. So WhatsApp ID is accessible. Even if you write open WhatsApp, it will not open. But if you say that send a message to this person on WhatsApp, it will send the message to web WhatsApp.com. So for open, you can do open YouTube, open Gmail. It will do it. And see, as I have written here first, I had searched for that mail thing. It had already composed. The
correct. It had opened.
Because
mails are linked to a certain.
Yeah, correct. I know. It will not specifically open the password academy while going inside. It will just show you the thing like password.
So you can basically search but not open properly.
Yeah, URL will open. Because URL is basically a path, right?
That's how we are getting it. Because URL links to your email.
Because URL is nothing but a path, right? Yeah.
You mentioned about Cloud API.
You will switch to a Cloud API.
Yeah, you want to switch to a Cloud? Okay, fine.
It will switch to Cloud API.
Will that become an API? Sorry? If you switch to Cloud, it will become an application.
Yeah,
then it becomes an application. No, because you cannot control unless you add something saying that only sending.
You have some safety features for like.
Yeah, you have it.
Yeah.
Hallucination. No,
I know. What a hallucination.
It's like
the thing is, if Olama hallucinates,
that's the thing. See,
Olama hallucinates.
See, like the other thing, the drag wala ke trouble. What keep it hit one drag but okay.
Yeah,
they have
not use any model APIs.
model APIs because we wanted to run locally